At its birth 4.5 billion years ago, the Earth is a gigantic ball of fire. Then it cools, making way for the appearance of the first oceans and the first embryos of continents. In the course of time, these emerging lands moved closer to one another. The oceans that separated them disappeared into the depths of the Earth's mantle. This phenomenon generated colossal forces. Under the surface, the temperature and pressure shot up like an arrow. In these extreme conditions, carbon crystallized in certain areas and was transformed into diamond. In South Africa, geologist Steve Richardson takes a great interest in these diamonds, a precious legacy of those past collisions. His research zone is located in Kimberley, in the province of Northern Cape, South Africa. On this site, we find what is called a craton, a zone which has not undergone any major change for several million or billion years. The Kimberley region is one of the oldest lands in all of Africa. And most importantly, it's precisely in this area that during our planet's infancy, two fragments of the Earth's crust collided.
This is a glacial pavement in the heart of the Kaapvaal craton. Deeper down, underlying the lavas, are even older granites that were produced by vertical differentiation of even earlier volcanic plateaus, which ultimately led to the production of granites and the formation of early Archean continental nuclei, which bobbed around on the Earth's surface by largely vertical movements. It was only when the Earth's crust had cooled sufficiently to make the crust more rigid that horizontal tectonics could take over. We have here in the Kaapvaal craton the first good evidence of the onset of plate tectonics, when the Kimberley block and the Witwatersrand block collided at some 2.9 billion years ago.
2.9 billion years, the estimated age of the first lands of the African continent. A number that Steve and his colleagues try to confirm with the help of diamonds present in the subsoil. These mythic precious gems brought fortune to Kimberley in the late 19th century. The story begins in 1867. A young farmer discovers a strange rock on a hillside. It is in fact the first diamond ever unearthed on South African soil. Baptized Eureka, it forever marked the history of the country. For years, prospectors from all over the globe set up shop in the region and dig the soil in search of riches. Today, a vast gaping hole attests to that scramble of olden days. Big Hole, 500 meters in diameter, the largest hole ever dug entirely by human labor.
This mine was started in 1871, and it took some 12 years for them to dig this hole down to a depth of around 200 meters. And it was a rich diamond pipe, and so the grade of diamonds and the quality of diamonds was very good, and so they decided that they needed to dig a shaft underground to further exploit those diamonds. As the hole deepened, it started to reveal the deep origin of diamonds, which until then was not understood. Prior to that time, diamonds were found mostly in alluvial workings. Here, as the hole went down, it went through the layers of geology and started revealing the outlines of a volcanic pipe, which comes ultimately from some depth of 100 to 200 kilometers down. And so this hole eventually was recognized as a volcanic pipe, which would have been erupted some 90 million years ago and breached the surface, which at that time was some 1 kilometer above where we are now.
The discovery of a volcanic pipe on the mine site gave scientists a unique opportunity to dive into the bowel of the Earth thanks to diamonds. These precious stones formed 100 kilometers underground. Much later, a volcano was born on this exact same site. The gemstones were thus pushed up, transported by a lava with a distinct makeup called kimberlite. Erosion then did its part, and over the course of centuries, the volcano disappeared completely. The diamonds are thus invaluable witnesses to past geological phenomena. Knowing their age means knowing the age of the rocks they were born from, the latter being inaccessible as they are buried in the depths of the Earth. Only a few rare specimens have been gathered from the volcanic pipe. They are carefully preserved here at the Big Hole Mine.
These are slices of the two main mantle rock types, eclogite and peridotite. They're very different compositions. If we look closely, in the eclogite, the garnets are a beautiful orange color, whereas in the peridotite, they're a purple color. And the reason why the peridotite garnets are so purple is that these are residual compositions from the removal of a melt that allowed for the stabilization of the carp-foil craton keel. Now it's these mantle rocks that have been carried from a depth of 150 to 200 kilometers that are the host rocks in which diamonds form. So we can talk about peridotic diamonds and eclogitic diamonds. And it's the disaggregation of these rocks that allows for the diamonds to be found in the kimberlite at the surface. And here I have a specimen of a diamond, an octahedral crystal of diamond, lodged in a piece of the original kimberlite magma from this volcanic pipe. Some of these diamonds have inclusions of garnet, either an orange garnet or a purple garnet inside the diamond. So the kimberlite is simply the train that has brought the diamonds to the surface as accidental passengers after they were disaggregated out of their mantle host rocks, the peridotite and the eclogite.
It's at the University of Cape Town in the Geological Sciences Department that Steve Richardson studies these diamonds in an effort to date them. The stones that interest the geologist are not the most precious. On the contrary, he only analyzes those that contain impurities. Infinitesimal slivers of rock inherited during their formation.
My ultimate aim is to date these diamonds based on the mineral inclusions that I'm looking for in these diamonds. It turns out that you can't date the diamonds directly, for example, by the carbon-14 dating technique, because that technique only applies to the last 50,000 years or so. Whereas we're talking about diamonds that are around 3 billion years in age. So I'm looking for mineral inclusions in these diamonds, particularly garnet, which I can identify on the basis of color as being from either eclogite, where the garnet is orange in color, or peridotite, where the garnet is purple in color. Once I've made those identifications, I'm then going to proceed to crack the diamonds to release the inclusions, which I will then dissolve to extract the trace elements that we use for dating prior to introducing the samples into the mass spectrometer.
Steve and his team have already studied more than 3,000 diamonds. For the moment, all the analyses concur. The stones are 2.9 billion years old. The Kimberley region does indeed lie on one of the oldest of African lands, the skeleton of the future continent. After it was formed, this first African territory grew little by little. Other islets of the Earth's crust collided with the craton and joined to one another over millions of years. But 2 billion years ago, a sudden and tremendous impact jolted the entire region. It took place in South Africa, where the little town of Vredefort is today located. Here, the landscape looks as though it's been tousled by the hands of a giant. Geologist Roger Hart has studied these rocks for years, decrypting the clues of the ancient disaster.
The rocks here are granites. This is a rock that is common throughout the world. But here at Vredefort, there's another component that indicates to us that something catastrophic has happened here. What we see here are these black veins and rounded boulders of granite, which are known as pseudo-tachylite breccias. The composition of the pseudo-tachylite is exactly the same as a granite. What we now believe is that the pseudo-tachylite and the breccias were formed through heat and friction. These pseudo-tachylite breccias are generally regarded as indicative of impact processes and are found at most craters worldwide. But here at Vredefort, they are particularly well developed, suggesting to us that Vredefort is a particularly large and violent impact.
Such a violent impact could only be caused by an object fallen from space. A gigantic meteorite, more than 10 kilometers in diameter.
What happens when a meteorite this size strikes the Earth? Well, firstly, you form a big hole. Secondly, this is immediately followed by rebound and uplift in the center of the crater, much like when you throw a stone into a pond of water and you get the central uplift. So if the crater here was 30 kilometers deep, you have a central uplift of about 30 kilometers. What happens to the meteorite? Well, it generally vaporizes, especially in a crater of this size and with this amount of energy. How big are they? What kind of explosion do they form? Well, in general, if you took all the world's nuclear arsenals and put them together, that doesn't even begin to compare with the explosion that formed at the time of Vredefort.
The meteorite burrowed a crater more than 300 kilometers wide and 30 kilometers deep. It's one of the largest and oldest craters on the planet. A lesion left by one of the most devastating disasters in Earth's history, the crater gives scientists unique access to the geological structure of the subsoil.
The rocks that we see here are sediments, quartzites to be exact. Quartzites like this are common throughout the world. In the normal sense, sediments and quartzites generally form in layers, horizontal layers. Normally these sediments rest on basement rocks, such as granites, and the granites normally rest on mantle, but not here at Vredefort. These are quartzites that have been turned vertical. In fact, what some of us believe is an entire 36-kilometer sequence of rocks has been turned on edge, exposing a vast section of the Earth's crust to view. Now, what is interesting for scientists is that this section gives us the opportunity to study the Earth's crust through geological time. What we believe is that these quartzites overlie granites, and that in the very center of Vredefort, we possibly have mantle rocks exposed. So we're talking a sequence in time going back to almost 3.6 billion years, the age of the rocks in the center. This is a very interesting concept for geologists because it allows us to study the chemistry, the tectonics, and the evolution of this crustal section in time and in space.
A veritable paradise for geologists, the Vredefort crater is a place unlike any other on Earth. Here, scientists have access to 3 billion years of evolution on a single outcrop. They can thus better comprehend the structure of the rocks that make up our planet. Roger has dedicated his career to the study of this meteorite. Even though it's not strictly speaking a tectonic phenomenon, its impact had the same effect. It transformed the face of the entire region.
Mountains can be formed in many ways. We know that mountains can be formed, for example, like the Alps, through tectonic processes. We know that volcanoes form mountains, like Vesuvius, but not here. These mountains are formed by meteorite impact. Meteorites are visitors from outer space. They are pieces of rock that are moving through our solar system and randomly impact anything that gets in the way. For example, you look at the moon is covered by meteorite impact craters. On Earth, we don't have that many. The reason you don't get that many craters on Earth is the Earth, unlike the other planets, which are dead, Earth is dynamic. Earth is living. Earth has plate tectonics. Plate tectonics destroys craters. Earth has erosion. Earth has water. The important point here, Earth is a dynamic, living planet.
Following this dramatic encounter with an object fallen from space, Africa experienced other upheavals. The land masses of the southern hemisphere continued to converge until nearly 800 million years ago they at last formed a supercontinent, Gondwana. Even today, the landscape tells the story of Gondwana's birth, a major episode in Africa's history. The Fish River Canyon is located in Namibia. At 160 kilometers long and 27 kilometers wide in certain parts, it is by far the largest canyon on the continent. This sumptuous scenery is one of French scientist Olivier Dutoit's work sites. This researcher's goal is to retrace the geological history of the region in its smallest detail.
We're here before a magnificent landscape that was sculpted by the Fish River, there on the valley floor. This river dug through a series of rocks, making it possible to now study their history, and also creating this magnificent scenery. This history begins about 1 billion years ago. So what are we looking at? At the bottom of Fish River, near the valley, we see layers that incline, like this. Those are rocks that have been deformed, metamorphosed, and heated. They formed during a collision which produced a mountain range. So imagine above us was a huge mountain range with very high peaks, several thousands of meters of altitude, like, for example, the Alps or the Himalayas. And it was those rocks that made up the continent we call Gondwana.
When they collided, the rocks of the former African and American continents crumpled to the point of forming a gigantic mountain chain. Water and wind then eroded the rock. Several tens of millions of years later, the mountain peaks disappeared, and the sea pushed into this area. Thus began a long phase of deposits on the seabed. Sediments formed successive even layers of strata. But a little more than 500 million years ago, a new tectonic thrust progressively pushed up the ground in the region. The sea then receded, revealing the multi-layered geological strata that the river would cut through bit by bit.
What we also see clearly are these horizontal layers, which means that for about 500 million years, nothing has happened in this region.
From the canyon's ridge, Olivier Dutoit can thus contemplate 1 billion years of West African history. At the deepest levels are vestiges of the collision of the continental plates during Gondwana's formation. Above, hundreds of strata are stacked up, revealing almost imperceptible variations. Tirelessly, the scientist crisscrosses the area and gathers a multitude of specimens from the rocks. Their analysis will one day make it possible to describe the infinitesimal movements that stirred the region until the present day.
It's interesting to understand why, in a zone that is known to be stable, we find quantifiable vertical movement, even if it's minimal. It's moved about 1,400 meters in 500 million years, enough to mold the entire landscape we see in Africa today.
The Fish River region is one of Africa's best to tell the story of the ongoing voyage of the continents. 700 million years ago, it was here that the future South American plate collided with Africa. During the same period, another phenomenon was taking place further north. A small fragment of land also collided with Gondwana. Traces of this event can still be found today in the Sultanate of Oman on the Arabian Peninsula. Sonia Roos and Melina Macouin are geologists at the Institute for Research Development in southwestern France. Their mission: gather the proof of this ancestral collision that dates back 700 million years. Their research zone is located on the coast of the Arabian Sea. In the heart of these desert landscapes, they seek out veins of a specific type of igneous rock called dikes.
Oh, look, you can see it there. Yes. Crops out nicely. So we stopped here to look at this large dike, which is actually an igneous intrusion that comes from the Earth's mantle. Magma from the depths moved through the crust and changed composition as it crossed through the Earth's crust, forming a vertical intrusion that appears on the surface.
In building this road, bulldozers exposed several dikes. But they also changed their structure. This forces the geologists to find another site to collect samples from. These veins of igneous rock formed 700 million years ago during the violent collisions of the tectonic plates. Inside these rocks, minuscule crystals containing iron can be found. It's precisely this metal that is of interest to the scientists. The Earth is in fact surrounded by a powerful magnetic field. Its inclination varies at every point on the globe. When the dikes were formed, the iron they contained literally became magnetized. The crystals were thus oriented precisely to the Earth's magnetic field at that time. The rocks then moved around the planet's surface as the tectonic plates moved. But the crystals in the dikes remained frozen in their original position. In this way, they memorized, as it were, the localization of the rock, and thus the continent, at the moment of its formation. We call this Paleomagnetism. To determine the ancestral position of this region, the scientists gather numerous samples along the coast.
So in the lab, we'll measure the paleomagnetic direction, which will give us an inclination, and we'll convert that into latitude. So we'll know at what latitude these dikes were formed. So 340? And 8.5. Our hope is that the samples collected during this mission will give us a position for time t. So not the whole story, but just the date of the intrusion of these dikes, somewhere around 700 million years ago.
Sonia and Melina carefully note the GPS position and, most importantly, the inclination of each specimen gathered. In the laboratory, the rock fragments are placed in a room that is perfectly insulated from exterior magnetism. An instrument then measures the orientation of the crystals inside the rock. Preliminary results seem irrefutable. 700 million years ago, when the dikes were formed, Oman was located at a latitude of 30 degrees south. This region thus was undoubtedly part of Gondwana. With the arrival of the future Arabia, all the pieces of the African puzzle began to come together. But in the southern region of the continent, near Cape Town, there's another event in the works. In the heart of the Cape Peninsula, the Table Mountain is the most famous vestige of a bygone collision. The plate that will later become Latin America enters into contact with West Africa. But in pivoting on its axis, it also butts up against South Africa. For John Compton, researcher at the University of Cape Town, this area is like home. He's roamed the cliffs of this massif for many years in search of new clues to the history of its formation.
Table Mountain is one of a much larger mountain chain. And this larger mountain chain formed at the time when Gondwana was forming. So from the west, we had South America, the continent, colliding with Africa. This produced large compressional forces of the collision of the two continents. So in that situation, when two continents collide, you have tremendous physical force of the two continents, and those tend to crumple and thicken the crust.
When the two continents moved closer together, the oceanic plate that separated them dove into the depths. Then the ocean disappeared, and the land masses were left face to face. They collided, and then continued to press against one another to the point of deformation. Between the two plates, gigantic reliefs then appeared. In the depths, granitic magma formed.
So the Cape Full Belt Mountains, of which Table Mountain is a part, formed from those collisions. So the northern branch to the north of us formed from when South America collided with Africa. The branch that goes to the east of Port Elizabeth formed when Antarctica collided from the south. So these two large continents joined Africa, and in that formation, all these rocks were crumpled up and formed into this folded mountain belt.
The Cape Fold Mountains run the entire length of the South African peninsula. They thus demarcate the zone where the continental plates collided. In the foothills, the violent collisions left other traces. Under pressure, the Earth's crust tore apart in several areas, allowing magma to rise to the surface. As it cooled, this magma turned into granite, a rock that is found all over the coast nowadays.
Behind me we can see Lion's Head, a famous monument in the Cape Town, where you can see the slopes of granite, and that same granite rock is exposed here along the coast. And this granite extends from here all the way south beyond Cape Point. It's a very large body, a large pluton of granite that's been emplaced here. You can tell it because it's very light in color. It has these very nice large crystals of feldspar in it that make it light in color, and it has intruded into this darker rock that I'm walking over now. And this darker rock is known as the Malmesbury group and was here before the granite intruded into it. So we can see this mixture of the contact zone between the granite rock to the south and this Malmesbury rock to the north. So I'm standing on part of that contact zone here, which includes this light-colored, large feldspar crystal granite and these ribbons of dark shale from the Malmesbury. So this sea point contact then is famous as both an example of deep earth processes. This is probably was happening at about 5 kilometers below the Earth's surface at the time. It has since been exposed here through the long process of weathering and erosion, and we now see it at the surface. So what happened here was that approximately 540 million years ago, this granite got intruded into and placed into the Malmesbury. And the reason that happened was because at that time there was no Atlantic Ocean here, but there was an ocean like the Atlantic called the Adamastor Ocean. And instead of spreading apart as the Atlantic is today, the Adamastor Ocean was closing. So what was happening was the oceanic crust was getting subducted beneath the African continent. And what we see here is sort of a freeze frame image of that intrusion of that molten rock into the solid existing Malmesbury rock. That meant that we had the closing of the Adamastor Ocean, and the continents were then joined together to make for a larger supercontinent, Gondwana.
"500 million years ago, the formation of Gondwana was complete. All the continental plates of the southern hemisphere were pressed up one against another. As for the future African continent, it could be found at the center of this supercontinent.
If we look to the west, we have the Atlantic Ocean Basin, very large ocean basin that has formed over those past 130 million years. At that time, South America, Argentina, Buenos Aires, was right next door to us here in Cape Town. And to the south, we have Antarctica, and then further to the east, we have Australia, Madagascar, and India. And all those continents once used to all be together as well as part of Gondwana.
even after the birth of the supercontinent, tectonic movement didn't stop. Slowly, Gondwana drifted across the surface of the globe. Thus, the tip of the African plate found itself at the South Pole. The Earth entered into a phase of climatic cooling, and a large portion of Gondwana was covered in a thick layer of ice. In the Damaraland region of Namibia, this period of glaciation left traces even in the heart of the savanna. Several years ago, Nicole Ulrich discovered astonishing fossils here. Hundreds of petrified trees, perfectly preserved for millions of years.
Oh, this is fascinating. Look here. It looks like a piece of wood, but it's actually a big piece of rock. It's the rock because of the process of petrification. These trees once grew in a cold environment nearly 300 million years ago. They were uprooted, maybe by water, by a big flood, and they were very quickly covered by a lot of sediments. And by this process, they were cut off from oxygen, and therefore they could not rot. And over geological time, in a very slow process, the wood material was replaced by quartz that crystallized in the sediments. This area here is regarded as the largest assembly of fossilized wood in southern Africa. If you look at this example, it's a perfect example. The structure here looks like a bark from a present-day tree. All the fine lines are very well preserved. This is absolutely amazing.
In analyzing these petrified trees, specialists noticed they were species typically found in Nordic countries. When they grew here, this area resembled parts of Canada. The climate was cold and humid, a far cry from Africa today. These fossils are thus irrefutable proof that 300 million years ago, Gondwana was located at the level of the South Pole. But sometime later, the supercontinent once again moved north. It's the end of the Ice Age. Temperatures rise, the ice melts, and enormous quantities of water sweep through the entire region.
Here we have three examples of big fossilized trees. These trees are all situated more or less parallel to each other. This means that they will have been transported by river in an old river channel. Also, the sediments around here that we can find indicate river sediments. These trees give even evidence of plate tectonic movements. 270 million years ago in Namibia, they were growing in cold climate, which indicates that the whole continent was situated further to the South Pole. Then, due to plate tectonics, the continents have moved away from the South Pole and from the Arctic climatic conditions, and today we have hot desert conditions in Namibia.
Today, these trees frozen for eternity tell us of Gondwana's voyage across the surface of the globe, and most importantly, of the intense climate changes the region encountered in the past. But the era when Africa is the center of the world comes to an end. Tectonic forces tirelessly continue to mold the face of our planet. After millions of years of living as a unit, the continents go their separate ways. Each one evolves in an entirely different fashion from the others. India will collide with Asia and thus create the Himalayas, the highest mountain range in the world. Australia will become its own unique ecosystem, an island continent isolated from the rest of the globe. Antarctica wanders to the South Pole and transforms into a frozen territory. South America veers west, becoming home to the longest mountain range, the densest forest, and the mightiest river on the entire planet. Less spectacularly, Madagascar moves barely 400 kilometers off the African coast. But over the course of centuries, the Great Red Island evolves into a distinct and unique world all its own. In the northwest of the country, in Majanga, a young researcher is studying the exact phase when Madagascar separated from Africa. Karen Salmons is a biologist at Northern Illinois University in the United States. For more than 10 years, she's traveled here every summer to study fauna in this region. Her goal, learn how and during which period animal species arrived on the island. In the field, her team methodically excavates the soil in search of fossils and tiny clues buried in the ground, which recount in detail Madagascar's history.
So Madagascar was part of Gondwana, so 200 million years ago it was connected to the rest of the land masses. And it was actually between Africa on one side and India, so it was wedged between the two. And about 165 million years ago is when it actually separated from Africa. So even though we think of Madagascar as being close to Africa, it severed its history with that landmass a long, long time ago. So it remained connected to India. And 120 million years ago, it moved approximately to where it is today. It was only 88 million years ago that it became completely isolated and it broke away from India. And then India went north towards the Himalayas to form the Himalayas. So Madagascar's been an island for really only it's been about 90 million years. And this is a long period of time, and it's much older than a lot of the groups that live there are thought to have evolved.
The animals living on the island reflect this very distinctive geological history. Separated from Africa and Asia for millions of years, Madagascar has become a singular ecosystem, home to dozens of species that exist nowhere else on Earth.
Madagascar has some of the most unique and bizarre animals on the planet, and one of the most unique things about Madagascar is the fact that almost all the animals that are found in Madagascar are only found there, so no place else on the Earth. So one of the most famous groups that people associate with Madagascar is the lemurs. Lemurs are a very interesting group of primates. There's more than 100 species now recognized in Madagascar, and they're only found on the island, so they're completely endemic. Now, what's interesting about lemurs is that people have hypothesized how can there be primates in Madagascar when the group primates, which is found in other parts of the world, is actually younger than the separation. So people have really struggled with this question. If they weren't stranded when the island was separated, and if they didn't come across from Africa in some way, then how did they get here?
Madagascar's climate and soil type aren't conducive to the preservation of fossils. Karen and her team thus instigate a multitude of dig sites in the search for new clues. For the moment, given insufficient data, the origin of lemuroids on the island of Madagascar as yet remains unknown. Today, 3 hypotheses vie to explain the arrival of the first individuals. The first is that these animals appeared a very long time ago, well before the separation of India and Africa. The second hypothesis is that with changes in sea level, an ephemeral land bridge formed between Africa and Madagascar, allowing the primates to cross dry land. The final theory is the most astonishing. Lemurs arrived from Africa on makeshift rafts, carried by the sea and pushed by storms.
Well, we know that even the last 10 years, we've seen some storms bounce between Africa and Madagascar, even just a couple of days back and forth. And some have actually reconstructed that you could make a journey in less than 30 days if you were stranded on a raft. So when we talk about rafts, it could be something like this, or even something much bigger. In fact, we see in other parts of the world, people have witnessed giant masses of vegetation, even 1 or 2 kilometers long, that are carrying trees and animals and even a little pocket of fresh water. So in fact, there's actually many different types of ways that these animals could have come to Madagascar.
The raft theory seems implausible, and yet today it is considered the most probable hypothesis within the scientific community.
Some have said, that's crazy, the chances of success are very small. But then the other side has said, well, that's true, it's very small. But if you have, say, 100 million years or 200 million years, that even something that has a very small chance is sure to be successful. And so there's been a big debate about whether this is actually a reasonable explanation. But, you know, we've really had to try to reconcile the fact that most of the groups we see appear to have evolved after Madagascar was already an island. So right now, that's actually the most supported hypothesis to explain their presence. So the best evidence always would be direct evidence. And the best direct evidence is to find fossils of the right age.
Perhaps one day we will discover how these primates found nowhere else on the planet took up residence on this sister island of the African continent. But already their mere presence demonstrates how greatly plate tectonics can influence the destiny of a region and the species that live there. Separated from the other continents some 90 million years ago, Madagascar has become a distinctive ecosystem, very different from that of Africa. But even today, emerged lands continue their perpetual voyage across the Earth's surface. Africa as we know it represents just an ephemeral phase in the history of our planet. A giant scar cuts across the eastern face of the continent, the Great Rift. From Mozambique to Turkey, little by little it tears Africa in two. In a few million years, a new subcontinent will be born, Arabia. In parallel, Africa as a whole continues to move north. Its collision with Europe and Asia will thus take place tomorrow, on a geological timescale.